Okay, so today I want to talk about thermodynamics. I want to focus on this information at a glance. While I talk about it, I'm going to discuss entropy. I'll be talking about free energy, and I'll talk about references to spontaneity. I'd also like to preface it by saying I'm also going to make references to the equilibrium constant, or K value. So let's get started. We'll start by discussing the first law of thermodynamics. Basically, it states that energy cannot be created or destroyed. This means that you cannot create something from nothing, and I've highlighted this before, but it just really speaks to the power that you cannot manifest something without something prior being in existence. All right, so let's tie this into chemical reactions. When we're talking about chemical reactions, there's a general scheme that you react A plus B that yields C plus D. But in order for that to happen, the potential energy has to be broken in the chemical bonds of compound A and compound B to create the product. In this particular example, it's highlighting that energy is given off, and the excess that's been given off is usually thermal energy or heat, which represents kinetic energy, which is therefore gone forward and transferred to everything that's surrounding it. So before we kind of get into more details, there's a little bit of recall. I want you to recall that delta H refers to enthalpy, and we've talked about it as relates to heat. And you want to understand that when you have a negative delta H value, you are dealing with an exothermic reaction where heat gets released. And you also need to understand that when there is a positive delta H value, it represents a endothermic reaction in which heat is absorbed. Now this is going to be very pertinent because we're going to be looking at some equations, and one of the things that you might be tasked with is looking at a particular balanced equation that features the heat element, and you have your states of matter, and you almost can infer whether the reaction would suggest likely having a certain value or if it might be perhaps even spontaneous. So let's get into this. A spontaneous process, and we're talking about spontaneity. It occurs without any outside intervention. One of the examples I use, and a lot of times when I'm talking about spontaneity, is that of examples like rust. It manifests, but it happens on its own right. It doesn't have to be heavily influenced by some type of man-made force. What also should stand out when we're talking about rust is another thing that highlights spontaneous reactions, which is that spontaneous processes don't have to be fast. They can in fact be slow, gradual progressions, but they just highlight that there's not a lot of external energy that's required to make them happen. So many forms of combustion are typically fast. However, if you think about another example where you're converting graphite to diamond, that is much more gradual and slow, and that's a spontaneous reaction. Now, kinetics is usually concerned with speed, but thermodynamics really focuses on that initial and that final state of what you're looking at. So, let's introduce a new term. Let's talk about this word entropy. Now, entropy represents a measure of randomness or disorder. You might think of it like chaos. The driving force for a spontaneous process is usually an increase in the entropy of the universe, which goes back to what are the laws of thermodynamics, and I'll highlight that too. In essence, the universe favors chaos, if you've ever kind of looked at the Jurassic Park movie and recalled that. So the idea of entropy is a thermodynamic function describing the number of arrangements that are available to a system. And that might sound wordy, and hopefully we can look more at kind of a practical sense of what we're trying to get at when we're talking about entropy itself. Nature tends to proceed toward the states that have the highest probabilities of existing. So those are early indicators. And kind of tying back into this law of thermodynamics, in any spontaneous process, there's always going to be an increase in entropy of the universe. Now, the entropies of the universe is increasing. It does increase. And for a given change to be spontaneous, the delta S value, which is a value for entropy of the universe, entirely must be positive. Now, there's an equation that ties the entropy of the universe together. That equation is represented below. Here you see that the entropy of the system, which is SYS for its content, plus the enthalpy of the surroundings yields the value of the entropy of the universe. And one of the things you want to think about is, suppose that you imagine the idea of ice melting. Well, as ice melts, you know that the ice could be the system and it's absorbing heat, which causes it to melt. But in this process, the heat is being removed from the surroundings and being cooled around the ice. So what they have is kind of a balance of your system and your surrounding, where one is giving and one is taking, and they represent the delta S of your universe. So you want to keep in mind that there's two forces at play here, and that equates to the entropy of the universe. Now, rehashing that example, when we're talking about entropy, why is it that when you leave that ice cube at room temperature, it begins to melt? Why do we get older and never younger? And why is it whenever rooms are clean, they become messy again in the future? Again, recapping, because the universe tends to favor disorder or randomness. We've highlighted this, but I want to reiterate, this is called entropy, or S. S is often given in terms of joules and not kilojoules. And this is important when you talk about calculations, which we won't get into the real calculations, but you'll want to make sure that you're cognitive of that, because I believe that the H value and sometimes the G that we're going to talk about for Gibbs can be referenced using kilojoules. Now, looking at the image, low disorder when they're iced. And then if you look at the image to the right, as it's melting, it's suggesting high disorder. So it brings together the impact of the state of matter on S, or entropy. So one of the things they highlight is that your S value, as a general sense, you can't give an accurate number assessment just looking at a state of matter, but you can get a general idea of how S is arranged, is by its state of matter. They term it microstates, and in fact there are several variations of microstates, but the ones we can focus on here, right there in the image, constitute solid, liquid, and gas. And what you should see as a trend is that as you look at the variation in the states of matter, wherever heat is added, basically entropy is favored. So you have your gases, which move exceptionally fast. They move in kind of a random order. They're always moving around. They have random collisions. But they're spaced out. They're spread out. They have a high degree of entropy. That's why you see kind of the double chevron sign highlighting the gases. Right below that, you have your liquids, and then you have your solids. So of all those, your gas is going to predominate in the high end of things in terms of entropy, whereas solids are less entropic. They are more ordered. They are more aligned. So that's how they are different in terms of their states of matter. Now, going back to that formula that I mentioned before when we're talking about entropy of the universe, you can measure the changes in entropy of the surrounding by looking at now how the heat flows. Now, the magnitude of entropy is definitely dependent on temperature. So when you change the temperature, you will affect the entropic value and therefore consequently affect the entropy of the surroundings. Now, the lower the temperature, the higher the impact to the surroundings of the transfer of energy. And remember, when we start talking about temperature, you're going to want to keep in mind temperature is measured using Kelvin, not degrees Celsius or Fahrenheit. And that's primarily because Kelvin is not a negative number. Now, entropy and exothermic processes. Entropy and a process being exothermic are related, but they're not exclusive to one another. They don't necessarily have to be both. And as a trend, you will look at that when you start looking at chemical reactions. So you want to be mindful of the fact that just because something is chaotic or favors disorder, it doesn't necessarily mean that it's going to give off heat in the process. Now, to reiterate what I said before about this relationship between enthalpy and temperature, we're looking at the delta S of the surrounding specifically. Notice there is a new equation here, and what this equation tells us is that there's a direct relationship, not a direct relationship, but there's a relationship between enthalpy and temperature. And so when we're looking at it, you're seeing that it represents negative value. So you got to think about it in terms of system versus surrounding. If you're talking about the surrounding, it's either, in the system, it might be giving off energy, and the surroundings might be absorbing energy. So again, we're reiterating that concept that one is happening and then the other is giving, one is receiving. So that highlights kind of how your values end up changing. So the entropy here concerns the surroundings. And like I said, your temperature wants to be in Kelvin. And we won't look at any particular calculations for this particular formula, but you want to understand that if you have a lower temperature, you're going to have a larger impact if you have a greater value for your enthalpy. And if you have a larger temperature, the variation in enthalpy can become moot. So there's another way of calculating entropy as well, and this is the entropy of a reaction. Here you see they've written kind of a 0 in the superscript position, and we're going to be looking at that. I've talked about it before, but if not, it represents entropy naught. And so one of the things you want to think about these values is they represent state functions. You want to think of them as being in scenarios where they have a certain set of conditions or criteria regarding temperature or in a state to relate them. Now, we've looked at this equation before, but here we're talking about the idea of calculating the entropy of a reaction. We understand that if you create more gases, entropy is going to be favored. However, if they give you values, you can mathematically calculate it by taking the entropy values of your products and subtracting the sum of the entropy values of your reactants to calculate the standard entropy of your reaction. So I've talked about it as being an extensive property that relates to the number of moles. So if you look at the comparison states of gases and you see that you have a scenario where you're growing your number of gas molecules, it's usually going to favor entropy. So this talks about how the more complex the molecule, the higher the standard entropy value. And, that's if we were doing like specific calculations. However, as a general scheme, you can really look at just how you think the entropy is going to translate. Here there's a classic example of a combustion reaction. And in this particular combustion reaction, it's highlighting that all of them are gases. And so that does matter. They're homogeneously related in terms of their states. And then you have 9 molecules of your gases and 10 molecules of your gases on the product side. And so because you're going from a lower number to a greater number, this shows favorability towards entropy. It also shows that entropy increases. Going back to the original equation, you'd be thinking of it in terms of products minus reactants, and the products would have a greater number than your reactants, theoretically. So let's tie that into the third law of thermodynamics. Basically, it says the entropy of a perfect crystal at 0 Kelvin is 0. So at 0 Kelvin, there is no disorder, since everything is in perfect position. So when there is no movement, or when you're at 0 Kelvin, there is no disorder. There is no entropy, and this means that your delta S is equal to 0. Now, tying in this idea of volume and perhaps even pressure to delta S, and this goes a little back to the kind of Le Chatelier's relationship. Enthalpy is not pressure dependent. However, entropy is. And entropy depends heavily on volume, so it also depends on pressure. Now, what does this mean? This means that entropically, things favor a larger volume because they favor having more space to randomly run amok, as opposed to a smaller volume, which confines them to limited space to move around. Now, if you want to look at it in terms of pressure, a lower pressure is preferred for entropic reasons as opposed to high pressure situations. And there are a number of analogies that can be used when relating this value of entropy. So let's jump on to another concept, because we just kind of talked extensively about this idea of entropy, and I mentioned the concept of spontaneity, but I want to try to tie it together. And the big tie-in here is this equation where delta G is equal to delta H minus T delta S. Now, delta G refers to Gibbs free energy. And, you know, if you want some history on it, it comes from Josiah Gibbs. He was a physics professor in the 1800s and contributed significantly to the world of thermodynamics. Now, enthalpy refers to our heat, our change in heat. T refers to temperature, and that has to be in Kelvin, can't be in degrees Celsius or Fahrenheit. And then delta S refers to a term that we've talked exclusively about up to this point, entropy. And so Gibbs free energy is really defined as the energy available to perform work. And G will actually determine whether a process is spontaneous. Now, what does this mean? It means this: if your delta G is negative, it means the reaction is spontaneous. I'm going to say that again because it's that important. If your delta G is negative, that means that the reaction is spontaneous. Now, as I highlighted before, spontaneous doesn't mean rapid. It doesn't mean it happens instantly. It means that the reaction will happen kind of on its own. Another way that people term this, especially in questions, is it'll mean that the reaction is thermodynamically favorable. A thermodynamically favorable reaction has a delta G value that is negative and spontaneous. So you want to keep that in mind. Thermodynamically favorable, negative delta G, and it equals spontaneity or spontaneous. And so this formula factors in enthalpy and entropy as well as temperature together. So the cool thing about this formula is when you think about it, there are things that can influence it. For instance, at absolute 0 for Kelvin temperature, you would have no disorder. And this would suggest that your delta H value would be equal to your delta G. Now, another way of looking at this is in terms of values. If you have a large delta H value, then it can overcome the value of your T or your delta S. Also, if you have a large enough T value, what you're saying is your T value or Kelvin is multiplied by your delta S. And so that can influence your delta G. And so instead of getting into math semantics, a lot of times they talk about these relationships in generalities. Now, before we talk about the generalities, you need to understand there are basically two methods of calculating delta G in a reaction. There's using the equation that we showed where you're comparing delta H and delta S using Gibbs free equation. And then there is basically a reiteration of the S reaction that I showed you, and some time ago, maybe if you've ever looked at it, the entropy reaction, where you're comparing the delta G of the products minus the reactants. And so those are the two primary ways of identifying your delta G value. Now, going back to the first method, what we want to understand is that the free energy tells us if those reactions will occur. Again, a negative delta G means it's thermodynamically favorable. It means that it's spontaneous. It will not tell us if a reaction is spontaneous. Again, it will not tell you if a reaction is spontaneous. So during a reaction, your reactant particles collide physically, and they must collide physically enough to break the bonds in a reactant to form new reactions. And we've looked at this as a relationship to delta H value, and some reactions require addition of heat energy. This gives the reactants the energy that they need to make sure that those reactions happen. So let's talk about delta G value as it relates to equilibrium. Well, if delta G is 0, the reaction is at equilibrium. Once again, if delta G is at 0, the reaction is at equilibrium. Now, if delta G is a negative number, it is spontaneous, therefore thermodynamically favorable. That means the reaction does proceed. It is favored to happen. Now, if delta G is greater than 0 or positive, this means that that reaction is non-spontaneous. It does not happen without some type of extra input or information or, source of energy happening. And like I said, if the delta G is 0, the reaction is at equilibrium. It's not moving forward or reverse. Overall, the multiple processes are traveling at the same speed. Now let's look at some energy diagrams. All right, so if you look on the left, you have kind of a spontaneous reaction, and the products have a lower free energy than the reactants. And that ties to that first equation where you're looking at the idea of comparing your products and your reactants. And therefore, your delta G value is going to be negative. Now, if it's right, then a non-spontaneous reaction occurs, and that is not a favorable reaction. It requires a substantial amount of activation energy to make that reaction happen. And so then you get into these terms of exergonic reaction and endergonic reaction. And so if you're looking at the two reactions, hopefully you're seeing that more energy is needed in the endergonic reaction than that of an exergonic reaction. So let's talk about the dependence on temperature. There are two terms in this equation when we're talking about Gibbs free energy. So spontaneity can change when the temperature changes, which we highlight when we talked about the idea of looking at disorder or spontaneousness reactions being influenced by disorder. The temperature and those values can impact spontaneity. Now, they are not necessarily correlated. This means that a reaction with a negative entropy or loss of randomness would be less spontaneous at high temperature. It doesn't want to happen, but it's pushed by the extra heat. So there are scenarios where one can overcome the other, is what's the take-home message from this relationship. And I really wanted to get to this early, but I'm glad I have it here. But I really want to just give you general values of how delta G can be impacted by the value of delta H and T delta S. And this is just more of a conceptual principle and not necessarily a governing body for all rules. If you wanted to really dive deep, you would look at actual numbers and try to solve from there. And to get a general sense, you can kind of predict the stream of conscious for reaction. So what this says is, all right, if we're given a value in the first row where your value of delta H is negative, this means you have an exothermic reaction and a value of T delta S that's positive, which means either your T is superbly large or your S is, kind of one of those entropy favoring kind of things, then your reaction will be spontaneous because it will yield a negative delta G. Now, how does this happen? Well, if you have the combination of math, you're looking at delta H, that's negative, and then you have a positive value for your T delta S. And so that makes it a spontaneous just off math principle, So if we look at the opposite, and you have a scenario where you have a value of delta H that is positive. Let's say you have an endothermic reaction, and then you have your T delta S value, which is negative. Well, we're not including the minus sign, so it's almost like adding two positive numbers together, which yields a positive value of delta G and therefore non-spontaneous. Now, the latter two are conditional arrangements, meaning that it can be spontaneous or non-spontaneous depending on the conditions. So if you have a negative value of delta H or a reaction that is exothermic, and then you have a value where somehow your T delta S value yields a negative number. Well, in order for that to yield a negative delta G, your T delta S must be basically lower than delta H. Now, what it's saying is that it's spontaneous if the absolute value of delta H is greater than the absolute value of T delta S. So basically, at low temperature conditions, in an exothermic reaction, that can happen. This is a conditional scenario where it would be spontaneous. Now, if you look at the bottom row, and you have two positive values, whether you basically have a situation where you have an endothermic reaction, and you have a T delta S that invokes a positive value. The only way it's spontaneous is if that T delta S value is greater than your endothermic value, absolute value. So spontaneous if the absolute value of T delta S is greater than the absolute value of delta H. So at high temperatures, this is achievable when you have two positive values. Now, questions that pertain to this chart are very popular. So if I were you, this is a premier piece of information that I'm writing down and I'm labeling in my notes. Now, standard state conditions, we've seen quantities such as entropy, and free energy are dependent upon the conditions present. When we're talking about standard state, we're talking about the set of conditions in which the materials can be compared. Pure solids, liquid gases at 1 atm pressure, they basically have a specific set of conditions. And so they're typically at 25 degrees Celsius, which is equating to 298 Kelvin, and they're designated by the not sign, similar to the degree sign, but it tells you that they have a specific set of conditions. And those are the set of conditions that they use to calculate the values for these G, S, and H. And so this is going to be important when we start looking at more calculations that talk about delta G, because what's different about this delta G is that it features that delta G naught, where you have the zero in the superscript. And it's the change in free energy that will occur if the reactant in their standard states are converted to the products in their standard state. So their states stay equally the same. And so here's the thing. Delta G naught cannot be measured directly. The more negative the value for delta G naught, the farther to the right the reaction will proceed in order to achieve equilibrium. So we're tying this into the equilibrium concept. Equilibrium is the lowest possible free energy position for a reaction. So now that presents a new equation that we want to kind of tie in and kind of finalize everything with. And this relates the idea of Gibbs free energy to G naught. So Gibbs free energy is related to G naught plus the rate constant, temperature, and the natural log of Q. Now Q is the reaction quotient. That's that products over reactants. And remember, the difference between Q and K is that K is at equilibrium and Q is that reaction at any state of any kind of conditions, whether it's an early stage, latter stage, prior to reaching the equilibrium. Now Q can equal to K, but when Q is equal to K, you have a scenario where you have equilibrium. And to solve these problems, you will use this universal gas constant here, where it's 8.314 joules per Kelvin. And you'll want to be mindful of your units. Temperature must be in Kelvin because you need a positive Kelvin value. And your equilibrium constant is your products over reactants. Your Q quotient, reaction quotient, is products over reactants. And again, that touches up on the idea that your Q doesn't necessarily mean it's at equilibrium. So if the system's at equilibrium, meaning there's no net movement, then you have a delta G naught value that is equal to 0, and therefore K is equal to 1. If the system is not at equilibrium, you can use Q instead of K when using this particular reaction. And so that pretty much